morning or good afternoon, depending on where you are. We are continuing with our lectures in thermodynamics. My name is Professor Duke Orata. Today we want to look at the principle of dynamic similarity. This is a very important principle in the sense that there are certain things which you are not able to determine empirically. You're not able to determine them empirically, in other words, through experimental means. And so you have to transpose information or data which you get in a system which you are able to handle systematically, and you know their values. For example, that's why we have small prototypes which you use to build bigger prototypes. For example, you want to know the behavior. You might want to do a small experiment, but then use that to design, for example, a heat exchanger. So principle of dynamic similarity is a very important concept, and we want to look at it, how we can apply it to forced convection in heat transfer. Remember, in our earlier lectures, and I continue encouraging you, humbly requesting you to look at our lectures systematically, we talked of two types of convection. There's the forced and there's normal convection. Now, in terms of heat transfer, one of the quantities which is normally easily measurable is heat transfer coefficient, and a lot of things are built around it. So today we want to look at what we call dynamic systems which have dynamic similarity. They have some sort of equivalence, so that if you know this, you can transpose that information to get information on that other system which you are considering as being dynamically similar. Now, one of the things which we can talk about is, let us look at as an example where we have a solid body, and this solid body, there's fluid flowing around it. And so we have a boundary, a hypothetical boundary. We have a boundary enclosing this solid body and the fluid flowing around that particular body. Let's look at it schematically. A schematic diagram. So we have a solid body. So that's a solid body. We have fluid flowing around it. Let's call this the boundary. Let's have another one, which is supposed to be dynamically similar. That's still a solid body, boundary. So we have our fluid still, this system. Let's call them A and B. So we have this boundary. This boundary is enclosing the solid body, and we have fluid flowing in that space there. And that space where we have the fluid flowing, we can call it a field. The region of fluid flow be considered as a field. And consider it as a field. Now, let us take some velocities. Let's say the velocity here is UA, velocity here is UB, and equivalent velocity here is UA prime and UB prime. Now, one of the first things is that we are assuming that the solid body and the boundaries are geometrically equivalent. Now, the assumptions is that one, the solid body and the boundary are geometrically equivalent. Of course, when you're talking of geometry, we are basically talking about their shapes, their mathematical shapes. Secondly, we are assuming that the velocity around the boundaries are the same, both in their size, that's the magnitude, in their direction, and in terms of the turbulence configuration. We have seen this diagram, you have it in your mind now, so we don't have to redraw it again. So the other thing we're assuming is that the velocity around the boundary is the same in both cases. It's the same both in magnitude direction and turbulence configuration. So basically, we're talking about the pattern of the turbulence. And the other assumption is that the temperature around this boundary is also the same. The boundary same. So what are we saying? The fact that these three assumptions are true does not necessarily mean that those two systems are dynamically similar. Please get that point. The simple fact that these are true does not mean that that system is dynamically similar. So let us push it a step further so that we get dynamic similarity for these systems, the conditions. So what are we saying? If we go further, then we are saying it doesn't matter whether the system is a turbulent system or a laminar flow system, then the following must also be true. For both laminar and turbulent systems, the following must be true for dynamic similarity. One, what are we saying? For that to be true, one of the things is that the Reynolds number in corresponding loss size in the field, the Reynolds number for corresponding state points in the field must be the same. And if the Reynolds numbers are the same, then it means that the velocities are the same at those corresponding state points in the field. Let's use this space. One, the Reynolds number for corresponding state points in the field must be the same in both cases. In both cases if velocity is to be the same. So anytime you see that the Reynolds number for corresponding state points in both systems are the same, then the velocities are the same. Remember, Reynolds number is density times velocity times the sum length times the dynamic viscosity. That's dynamic viscosity that's length. It can be diameter. So if we assume that our solid body is a sphere, then we'll be talking of diameter. Then this is velocity. And of course, this is density. That's Reynolds number. The second thing is that if the temperatures are to be the same for corresponding state points in the field, then the Prandtl number must be the same. If the temperature at corresponding state points in the two systems is to be the same, then Prandtl's number must be the same. Be the same. And what is Prandtl's number? Prandtl's number is dynamic viscosity times the isobaric heat capacity over thermoconductivity. Remember, K is thermoconductivity isobaric heat capacity, and that is dynamic viscosity. That's dynamic viscosity. So it is only then that the temperature at the corresponding state points in the field in both systems will be the same. And of course, when we talk about Prandtl's number, then the other important quantities also comes in. That's the Nusselt number comes in. And so the Nusselt number in the elements around that solid body for the corresponding state points must also be the same if the Prandtl's number and Reynolds numbers are the same. What was Nusselt number? So we are saying, number 3, the Nusselt number must be the same for elements or state points on the solid body if Prandtl number and Reynolds numbers are the same. And remember, we had this in our other lectures. We saw that the Nusselt number, Nu, that's the Nusselt number, divided by the Prandtl's number and Reynolds number, gave us what we call the Stanton number. And so let's have a look and see what the Nusselt number is in a nutshell. Let's look and see what the Nusselt number is in a nutshell. So what are we saying? Therefore, the Nusselt number on rearrangement The Nusselt number is the Prandtl number times the Reynolds number times Stanton number. Prandtl number, we know. Reynolds number, we know. And Stanton number, we know. Stanton number, we know, is that quantity there. Prandtl's number, Reynolds number, Stanton number. Remember, H is the transfer coefficient. So you can see that the dynamic viscosities have cancelled. Isobaric heat capacities have cancelled out. What else cancels out? Density has cancelled out. Velocity has cancelled out. What are we left with? We are left with HL over K, and that is Nusselt number. So, when these quantities are constant, we say the two systems are dynamically similar. Therefore, when Prandtl's number are the same, the two systems, then they are dynamically equivalent. And of course, we are making some assumptions. There's a generalized assumption, which is normally not very correct, but is assumed that the physical properties of these fluids do not change with temperature. Not, it's just an assumption. It's assumed the physical properties of those fluids don't vary with temperature. They vary with temperature. Of course, that's a tall order, but we always assume they don't vary with temperature. So, when two systems are dynamically equivalent, it can help you design that other bigger system, which probably you want to work as you're designing it with small models, small prototypes, which you will actually use to transpose the information you've gotten here to compute data involving the bigger models. So dynamic similarity is a very important principle, very, very important principle in design. So we'll stop at that point. We'll continue next time with our lectures.